Today we discuss a new concept of Ampere's law. That's very important in board exam and also JEE NEET exam. So here at the starting we discuss of Ampere's law. Okay. Is that very important in modern communication because the Ampere's law is one of the key member of Maxwell's law. Okay, so Ampere's law, Gauss's law, and Faraday's law. These are the very important to making that Maxwell's law. So previous class we discussed a Biot-Savart's law application. Okay, I borrowed some concept from Biot-Savart's law, and we know that the dB, that magnetic field, if I consider a vector or a magnitude consider, now we consider a vector dB, that is mu 0 upon 4 pi ideal cross r, and here is that r square. That's the vector form of Biot-Savart's law. Okay, so application of Biot-Savart's law we borrowed from that concept. A magnetic field, a long straight wire. So magnetic field, application of Biot-Savart's law. The application is magnetic field of a long straight wire okay. Now we take a straight wire. Suppose we consider that's the straight wire. Okay, current goes in that direction, upward direction. Okay, and calculate magnetic field at surrounding of that wire. Suppose we choose any point in surrounding. Choose suppose a point, arbitrary point P here. Point P. When we apply a right hand thumb rule, so thumb represent that current and curl of other forefinger represent that magnetic field. So if the thumb is aligned at the current where, so other forefinger is curled, so the magnetic field at point P here is towards that board. So that's why it was the cross. Okay, so B is towards the board. Okay, and we choose a differential length here. Suppose there is a length of the wire B, that's called L, the length of the wire, and I choose a very small length here. Suppose this length is called DL, the differential length. Okay, and derivation is another way. Previous class derivation is method 1. Here we put the derivation is method 2. Both are correct. Okay, I choose another method. Okay, I borrowed this method from Resnick Halliday. Suppose so you join these. Too much typical to drawing this line, but I can now consider as a straight line. Okay, it's not look like a straight line, but you imagine that a straight line. So distance is here that r, and that's angle here. The angle is theta, and from there is the origin point. Suppose these are the called capital R, mean the capital R. Okay, and suppose that's now if that's the length of the wire be the S, so the differential length is now ds, and consider this length be the same. Okay, we choose just only this length. Okay, the S, this part of wire. Okay, from starting to this part, and these are the differential length. Here the calculator Biot-Savart's law. Here from equation we know that dB, that is equal to mu 0 upon 4 pi I ds sin theta by here, that's the r square. From differential length to point P, the distance is r square. These are the small r, not capital R. Okay. Now here you see that if I choose that the origin point here, so that's from 0 point or the one dimension, that is a 0. From 0 to upper part means 0 to infinite, and below there that's also that 0 to negative infinite, or I think these two lengths are the same if I consider only magnitude. Okay, so from 0 to infinite, or here minus infinite to 0, suppose there are two integrations, so we get a final B magnetic field. The two part, both their magnitude will be the same, you consider. So that is we put the one integration here, 0 to infinite or minus infinite to 0. Actually the both the length be the same. Okay, the integration limit be the same, the gap of these two limits. So upper part was 0 to infinite, lower part is the upper part, that is the lower part, but we choose the both are the magnitude be the same, so calculation obviously is same. So just calculate magnetic field and multiply it by the 2 to get final answer. So dB. Now we put dB here, 2 mu 0 upon 4 pi is that a constant, so outside the integration. So here I ds sine theta by r square, here is the limit 0 to infinite. Okay, so here you see that how to solve this type of integration. So 2 mu 0 upon 4 pi. Okay, so I obviously the outside here the integration I also be the constant here. Now here the ds, that is the r square, basically ds is present where the integration. Now here the important is sine theta. These angle with the theta, and these are the straight lines, so 180 degree means pi, these angle with a pi minus theta. And we know that, from class 12 or class 11 trigonometry, sine theta, that is equal to sine pi minus theta. Okay, so both be the same. So if sine theta and sine pi minus theta be the same, so ds sine theta means this also be the same angle obviously. So perpendicular by hypotenuse. So here the perpendicular is that r, okay, and here is the hypotenuse. Perpendicular always choose the opposite of the angle. Okay, opposite of the angle is the perpendicular, and here the 90 degree, that's the angle is 90 degree. Opposite of 90 degree is the hypotenuse. You know that. Okay, now sine theta here perpendicular, because that's the angle, so that is a perpendicular by hypotenuse, that is a capital R by hypotenuse r small r equal to root over of a square plus capital R square. So a square plus capital R square, here is the root, that is the sine theta, we get sine theta 0 to infinite limit, and 1 over r square, and r square means a square plus r square from Pythagoras theorem, we know that, and here is the ds. So final expression now we get 2 mu 0 times I by 4 pi 0 to infinite r upon a square plus r square. Here is a half, okay, and as a 1 half plus 1 we get 3 by 2, okay, that's term is ds. Okay, now we solve this integration with some class 12 concept or integration concept here. Let's take some assumption. Let say that is a is equal to r tan theta, is equal to r tan theta. Now here the ds, that is equal to r tan theta differentiation, we say ds by d theta here. Differentiation both sides with respect to theta. So tan theta we get sec square theta. So ds equal to we get r sec square theta d theta. We put ds here. Now check the limit. Very important, check the limit here. So here we get 2 mu 0 I by 4 pi, changing the limit 0 to infinite now changes to 0 to pi by 2, 90 degree. When I put s equal to 0, so tan 0 degree will be 0, and here when I put s equal to infinite, so tan pi by 2 get infinite. So lower limit be the 0 and upper limit be the pi by 2. Okay, so a square plus r square. So here a square plus r square. Okay, so here a square means r square tan square theta plus r square. So r square taken common, so tan square theta plus 1. So tan square theta means sec square. R square sec square theta. Okay, so in bottom of that equation we put a square plus r square. So here we get r square sec square theta whole to the power 3 by 2, and we get put r here. Okay, and ds we get r sec square theta d theta. So that is equal to 2 mu 0 I by 4 pi, and integration limit 0 to pi by 2 here. So get r square sec square theta d theta by r square sec square theta. R square 3 by 2 means here is the r cube actually. So sec square cancel with theta square, and these two are the cancel, so we get sec cube theta. So square and square cancel, these cancel. So finally we get 2 mu 0 I by 4 pi. Okay, so these r is outside the integration because there is a constant. So 0 to pi by 2 we get 1 by sec. 1 by sec means that is a cos theta d theta. If I choose the cos theta integration, so integration of cos theta we get sin theta 2 mu 0 I by 4 pi r. We get sin theta, so sin theta 0 to pi by 2. So sin pi by 2 the 1, sin 0 0. So finally we get 2 mu 0 I by 4 pi r. These two cancel. The final expression we get b equal to mu 0 I by 2 pi r. That's the final expression of magnetic field as a unit is Tesla. Okay, that's a very important formula. We get magnetic field. Okay, the current carrying wire surrounding by the wire generate a magnetic field, or calculate that magnetic field with help of Biot-Savart's law. With the help of Biot-Savart's law, we derive that Ampere's law. Very important. Now start from this help, we derive that Ampere's law. Actually, that's today's main important topic is Ampere's law. Okay, suppose we consider a loop here. Okay, and current direction, suppose a clockwise current direction. Choose a loop, circular loop, current in that direction, clockwise. So clockwise current direction. Now the magnetic field. We put a differential length dl. Okay, that's the dl. Okay, that's important. That's the differential length dl. We put dl. So idl in that direction. So if ideal, thumb represent the ideal direction, and other forefinger, if we curl off other forefinger, we bend that, so we get magnetic field. So magnetic field B here is a cross inside the board, and here is a dot. Okay, Now if I join these two lines, look like a circular. Okay, these look like a circular. Here is the magnetic field in that direction. Here is magnetic field in that direction. B. And this red color loop, this loop is called Amperian loop. Yeah. Loop. Obviously a closed loop, one dimensional circle. And this Amperian loop, there is a this loop enclosed it is a charge current carrying wire I, current passing through that wire. Okay. Now from this loop is Amperian loop, close a wire. Okay. Face obviously is a closed line, not okay. This is not a this is not a surface, it is a closed line actually. The Amperian loop is a closed line. Okay. And here we choose a small length ds. Okay, length ds. In Amperian loop there is a line, and ds obviously the same direction or b direction. B and ds both are in same direction. So if I integrate b closed line integral b dot ds, b dot ds, these are the line, close a line. Okay, the line here. So we get b equal to suppose there is a two dot product here, the vector dot product. So b ds cos, both are in same direction, cos 0 degree, cos 0 be the 1. So cos 0 1 we get b ds. Now this outside the integration of ds, so we get finally s. Okay, finally get s. Now the s. Now we choose, if I that a center, if I choose as a center of that this green color loop, and we say that radius b that is called r, and these are the circular loop, obviously these radius obviously the r. So now s is replaced by b times 2 pi capital R. Okay, b equal 2 pi capital R, and here we see that b 2 pi capital R, here we get b 2 pi capital R from this expression. Why I derived that equation here today's, that's the important. This just only one step, we use just only one step. B 2 pi R that is equal to mu 0 times I, we put here b 2 pi R that is equal to mu 0 I enclosed by that loop. This I enclosed by the Amperian loop. If that loop is a circle or any shape, okay, I choose circle because we know that the circumference of the circle. If you choose any arbitrary length, it is difficult to calculate the circumference. That's why I choose a circular loop. That's the Ampere law. We get closed integral of b ds. Okay, ds is not stands for a surface, it stands for a line. Okay, that is equal to mu 0 I enclosed by the Amperian loop. That's very important. That's the Amperian loop. That's the Ampere's law actually. The Amperian loop actually are the note here. Note the Amperian loop. The Amperian loop must be enclosed current. Okay, so here this is important net current. These are the net current. How to describe the net current? Suppose you choose a, suppose there is a Amperian loop look like this. These are the Amperian loop. Okay, and here is the three current passing here. Suppose one current in upward direction, one current is downward, other current is upward. Suppose there is I1, I2, and here is the I3. This purple color Amperian loop includes only two current direction, I2 and I3. Suppose we choose a magnetic field here in that, suppose a magnetic field in that direction, say that be in that direction. So apply the right hand thumb rule. If curl of that direction, so our current direction is upward. Okay, that's the original current direction is upward, and that's the downward. So when we apply right hand thumb rule, the I3 is satisfied, but I2 is not satisfied. So I3 choose a plus, so I2 choose a minus. Okay, if I put a right hand here, okay, there is a thumb and other forefinger here. Okay, now that the final expression of Ampere's law is B dot ds, okay, close, not a surface integral, there is a line integral, obviously. Okay, there is mu 0, I3 be the plus and I2 be the minus. That's the Ampere's law. Then for enclose the net current, if you have more than 2, 3, 4, 5 any value, okay, must be that line is enclosed some current. Okay, enclose, that is a one dimension obviously. Okay, enclose some current where, current passing the where, that's very important. Okay, that's the Ampere's law. Okay, and here is that choose and some assumption here to calculate the application of 1 Ampere's law. Application of Ampere's law. Okay, so here we choose that these are the cross section view of a wire. Okay, the current passing through the wire, that's the cross section view, and the dot represent these dot current direction is towards me. Leave the whiteboard and there's a direction towards me. Okay, now choose that first here magnetic field outside the long straight wire, outside the long straight wire. So here the outside, so you choose the Amperian loop is outside of that wire. Suppose we choose Amperian loop. Suppose you choose the Amperian loop here. This blue color line is the Amperian loop, and this look like a circle. Okay, and not a, this look like a circle. Now we assume that this is a beautiful circle. Okay, now and that's a wire surface. These are the wire surface. This is okay. Remember now this length. Okay, the Amperian loop. These are the Amperian loop. This length we choose that small r. If current I is towards me, so magnetic field is anti-clockwise direction. Towards me means magnetic field is anti-clockwise direction. Suppose the B in that direction. And choose a very small differential length of that Amperian loop is ds. Okay, now apply the Ampere's law here. Suppose integration B dot ds mu 0 I enclosed by that Amperian loop. Very important. Okay, so B and ds both are in same direction, so cos 0 with the 1, so you get B indication of ds, that is mu 0 I enclosed. So we get bs mu 0 I enclosed. So finally b equal to mu 0 I enclosed by s. And this s is the circumference of that circle. This Amperian loop is choose a one-dimensional circle. The circumference of the circle is a 2 pi r. 2 pi r. Okay, that's the final expression. That's the Tesla. This is a magnetic field outside the long straight wire. Okay, and another is a magnetic field inside the long straight wire. Same diagram. Magnetic field inside the long straight wire. Choose an where this is a cross section view of this circle is not good. I think this circle is look good. There is some okay, very good. Okay, these are the cross section view of the wire, front view. Okay, and there's the current direction is towards me, okay, and that's a wire surface, and we choose that Amperian loop inside that conductor. This line is the Amperian loop, okay, and we choose from I to that's the small r. Okay, if I is towards me, similar condition here. So magnetic field B, okay, that's the anticlockwise direction. So here that's the B here, B in that direction. Suppose I choose a small differential length dA, same in same direction. Okay, and that's the R, capital R, radius of that cross section view of the wire, conducting wire. Here we see that the some part of current passing through in that Amperian loop, inside that Amperian loop. Total current, here is some part of total current crossing that Amperian loop. Okay, that's very important. Now we apply the Ampere's law here. So B dot ds mu 0 I enclosed, that's very important term here, I enclosed, and BDS we get similar concept, both are in same direction. So BDS is a cos 0 be the 1. So indication DS, so that's the S mu 0 I enclosed. Okay, this I enclosed is not equal to the total current I. You remember that. That's a very key point here. This I enclosed is not equal to that capital I. Okay, so here B equal to S. S means here the surface, and there's a circumference of that Amperian loop is 2 pi smaller. Mu 0 I enclosed by 2 pi smaller. So I enclosed is the some part of the current is enclosed by the surface. So what is the I enclosed? Total current I. Okay, some parts means I, here you see that the cross section view here actually. So here is the surface area. There is a surface area, that is a pi small r square by pi capital R square. That's the I enclosed. Now we replace B equal to mu 0 by 2 pi r, that is I, total I by pi r square by pi capital R square. That's the B. Now if I cancel these pi, here these are, we get B equal to mu 0 I small r by 2 pi capital R square. Okay, that's the final expression. Okay, and here you see that the B, magnetic field B, is inversely proportional of 1 by R. Okay, in outside the conductor, if R is increased, so magnetic field is decreased. Okay, okay, outside the conductor, and inside the conductor, and B is directly proportional to the R. Means the center have zero magnetic field. Center have zero magnetic field, means R is zero, so the magnetic field will be the zero. Now you draw a graph, a basic graph, for analyze the graph, help of graph. So B, and here is the R. At that point is small r equal to capital R. Capital R is the radius of the conductor. So maximum magnetic field will choose here. Surface of the conductor. Maximum magnetic field B max, where the surface of conductor. That's that important point. Maximum magnetic field at the surface of conductor. So outside the conductor, they are inversely proportional. So outside the conductor is look like this, and inside the conductor, there is a straight line. Okay, so that is B directly proportional to R. Here is the inside of conductor of where. Here is B 1 over R square outside of conductor or where. Clear? What is the Ampere's law? Now how to derive the Ampere's law? So today in the class here, if any doubt in that portion, always ask in comment section. I will try to give the answer. You remember that. That's a very important in board, JEE and NEET exam. Okay. So don't skip that part. Okay. So study thoroughly, and basic there is a very easy chapter part in class 12. Okay. So today in the class here, next class we discuss new topic and new discussion. Thank you.